Hello everyone, this is Dr. Webb, and welcome to this abstract algebra video. If you recall, when we were talking about groups, we talked about group homomorphisms, and those are maps that preserve the group operation, map from one group to another group that preserves the group operation. And so now we're going to talk about homomorphisms involving rings, and the idea really is going to be very similar. So what is a ring of homomorphism? Well, let's let R and S be rings, and then a function phi from R to S is going to be called a ring homomorphism if it preserves both of the ring operations. So for any A and B in R, we have that phi of the sum of A and B, so phi of A plus B is going to equal phi of A plus phi of B. And phi of AB, so phi of the product, is going to equal the product of phi of A and phi of B. Okay, and so this flows in exactly the same way as the definition for group homomorphisms. It's just now we have one more operation. And so ring homomorphisms are going to preserve both. Okay, so here are some quick examples of ring homomorphisms. So one is if we start from the integers, then the map that sends k to k mod n for some positive number n is going to be a ring homomorphism. And that's just because, as we've seen before, the addition and multiplication, the arithmetic from the integers flows well into the arithmetics in z mod nz. It works exactly the same way. An important homomorphism from a polynomial ring, so if you have R of x as a polynomial ring, then the map that sends the polynomial f of x to f of a, where a is some element of the ring, is going to be a homomorphism. And so this is what's called an evaluation map. And so what the map does is it really is plugging in a value for x there. And as you've seen before, the arithmetic with polynomials works well when you plug values in. So for any ring R that has positive characteristics, so the characteristic is not 0. Remember, the characteristic means that for any element, this prime characteristic P, this means that for any element in the ring, if we do add A to itself P times, we end up with 0. Okay, and so that's what characteristic P means, and we need this characteristic to be prime. Then there's a map that sends any element A in the ring to A to the Pth power, and this turns out to be a homomorphism. And so really the big idea here is if the characteristic is P, if you look at A plus B raised to the Pth power, well, if you use your kind of binomial theorem, this is going to be A to the P plus P choose 1, A to the P minus 1, B plus P choose 2, A to the P minus 2, B squared, all the way down to P choose P minus 1, A, B to the P minus 1, plus B to the P. And so this is coming from the binomial theorem, which you've seen before. But in this case, all of these binomial coefficients, except for the first and the last one, except for the ones, these are all divisible by P. These are all multiples of P. And so if P times anything, if anything added to itself P times is equal to 0, then these terms in the middle all disappear. So these are all equal to 0, and we're left with this equaling A to the P plus B to the P. And so this is a very special map when you're in characteristic of a prime P. And this is what the fancy name for this is. This is called the Frobenius map, named after a mathematician in the 1800s named Frobenius. So an example of something that's not a ring homomorphism is the map from the integers to the even numbers, sending n to 2 times n. This is not going to be a ring homomorphism. And quick reason for this is that if you do 1 times 1, that should get shipped to 2. But if you do 1 times 1, where you apply the map first, then you get 2 times 2 is equal to 4. And so these two do not equal each other. So this is not a ring homomorphism. So a couple of quick definitions that will make a lot of sense. If you have a ring homomorphism that's both 1-to-1 and onto, this is called a ring isomorphism. So if you recall that group isomorphisms are group homomorphisms that are 1-to-1 and onto. So this follows the same idea. Furthermore, if you have a ring or isomorphism from a ring to itself, then we'll call this a ring automorphism. So same as we saw with groups, a group automorphism is an isomorphism from a group to itself. A ring automorphism is a ring isomorphism from a ring to itself. Okay, so now let's talk about some basic properties of ring homomorphisms. You will notice that these mirror very closely to the group properties of group homomorphisms. And so for the most part, we're not going to be proving these because the proofs are essentially the same. Or you have to just show it for 2 operations rather than 1. But because homomorphisms preserve the group operations, it works very much the same way. So first of all, for any element in the ring and any positive integer n, recall that this n times r, what this really is shorthand for, is r plus r plus r n times. Then that's the same thing as adding phi of r to itself n times. And if you do phi of r to the nth power, so r times itself n times, then this is the same thing as getting phi of r to the nth. And so this follows completely from the fact that ring homomorphisms preserve these operations. If we take a subring of R, so if A is a subring of R, then the image of A is going to be a subring of S. And so what this means in particular, one result of this, is that if R is a ring homomorphism, then the image of the map, phi of R, this is always going to be a subring of S. In general, these will not be, if phi is not onto, then in general, the image of the whole ring will not be an ideal, but it will be a subring. On the other hand, if it is onto, if phi is onto, and I is any ideal, then phi of I is going to be an ideal. And so again, the fact that phi is onto here, this is critically important for this to be onto, because you need the fact that anything that you multiply to it in S is in the image of the map. If J of S is an ideal, so if J is an ideal of the image of S, then the preimage of J is going to be an ideal of R. And so one of the things to check to make sure this is ideal is that the preimage needs to be non-empty, but since any ideal contains 0, then the preimage of 0 has to be 0. And so that means that at least you have the preimage is it can at least be, is at least going to be the trivial ideal. If R is a commutative ring, then the image of R is going to be commutative. So notice that this doesn't mean that S is commutative. It just means that the image of the map is commutative. And so since phi of R is going to be a subring of S, it lands in some commutative subring of S. If R has a unity and phi is onto, well then that means, and S is not the trivial ring, then phi of 1 is going to be a unity of S. And so in particular, this means that S has unity as well. So it's important to note that S is not the trivial ring. There is always the trivial homomorphism between rings that sends everything in R to 0. So that is always a valid homomorphism. And so it's important for S not to be just 0, that it has other elements in it. And again, we need phi to be onto here to guarantee that phi of 1 is the unity of S. In fact, if phi is not onto, then, and S is non-zero, so important to note, if phi is not onto, there may exist homomorphisms that are non-trivial, where phi of 1 is not the unity of S. And so this is kind of this can be an interesting thing. It'll be a unity of the subring, but won't be unity of the whole ring. And so this is kind of a fun fact to explore. If phi is an isomorphism, or phi is going to be an isomorphism, if and only if phi is onto and the kernel of phi is trivial. So the kernel of phi is just 0. And so what this boils down to is that the kernel of phi is just the trivial ideal, just 0, if and only if phi is 1 to 1. And so this is real easy to see if, especially going in the forward direction, if phi if the kernel is only 0, then, and you have phi of A equals phi of B, well then this means that phi of A minus B is equal to 0 in S. So let's put an S there, because the 0, one of the properties of being a homomorphism is that 0 has to be mapped to 0. And so if that's the case, and only 0, so only the kernel is only 0, then that means that A minus B is equal to 0 in R. So A is equal to B. So that's one direction. So for the other direction, showing that if phi is onto, well then let's let A be in the kernel of phi. Well then phi of A equals 0 in S, but that's also equal to phi of 0 from R. And so since phi is onto, this means that A is equal to 0 in R. So the kernel of phi is trivial. Everything in the kernel has to be equal to 0. Okay, and lastly, if phi is an isomorphism from R onto S, then same as we saw before with group isomorphisms, then there is an inverse map, which is also an isomorphism from S onto R. Okay, so any isomorphism between rings means that there's also an inverse isomorphism between the rings. Okay, so here's a couple of theorems that we're not going to prove right here because these are going to be homework problems. But these actually, the statements of these mirror the statements of results from group homomorphisms. And so you actually can, to do these problems, you actually can go back to how we proved it for group homomorphisms and just adapt it for rings. Right? So the first one is that the kernel is always an ideal of the domain. And so if phi is a ring homomorphism from R to S, then the kernel of phi is an ideal of R. And so this gets back to what we talked about at the beginning when we were talking about ideals, that ideals sort of mirror normal subgroups, where for group homomorphisms, we saw that the kernel of a group homomorphism was a normal subgroup of the domain group. For ring homomorphisms, the kernels are going to be ideals of the domain ring. Then we have, similar to the first isomorphism theorem for groups, we have a first isomorphism theorem for rings. And so this states, let R and S be rings, and let's let phi of R to S be, phi that sends R to S be a ring homomorphism. Then there's a mapping phi bar that sends, which is, the domain now is R modded by the kernel of phi, gets sent to the image of the map, where the coset R plus the kernel of phi is mapped to phi of R. Then this mapping is going to be an isomorphism between R modded by the kernel of phi and the image phi of R. Okay, and so again, this mirrors the first isomorphism theorem for groups that said if G is a homomorphism, then G, if there's a homomorphism from G to G prime, then if you do G modded by the kernel, that's going to be an isomorphism to the image. And thirdly, if we have a ring R and we let I be an ideal of R, then there is a natural map. So we call this actually the natural map from R to R mod I that sends phi of R to the coset R plus I. This is a ring homomorphism, and the kernel of this map is I. And so in this sense, this means that not only are kernels going to be ideals, but every ideal you can think of as being a kernel of some homomorphism. And so this is actually one of, this idea that ideals are the kernels of ring homomorphisms. This actually gets to one of the sneaky ways to prove that something is an ideal. You actually create a homomorphism and prove that this set that you think is an ideal is the kernel of it. Okay, so now let's get to some theorems that we will prove right now. So first, let's let R be a ring with unity. Then there is a mapping from the integers to R that sends phi of n to n times 1. So this is, again, you're thinking about this as being, if n's positive, we're thinking about this as being 1 plus 1 plus 1 n times. If n's negative, we're thinking about it as being negative 1 plus negative 1 minus n times. Okay, so proof of this, there's really not all that much to prove here. Most of the work has already been done. And so if, so R here, this is our image, or this is our codomain for this map. And so we've seen before that if we do m times 1 plus n times 1, this is equal to m plus n times 1. There isn't really very much to do here. If you're adding 1 together m times and then add n more 1s to that, then it makes sense that you end up with m plus n total ones. And another thing that we proved in homework is that if you do 1 plus itself m times 1 plus itself n times, you end up with 1 added to itself and m times n times. And so this is another thing that we've seen before. And so in the first line, this is equal to, this is the same thing as saying that phi of m plus phi of n is equal to phi of m plus n. And the second line is the same as saying that phi of m times phi of n is equal to phi of m times n. Okay, and so these are the two statements we had to show that were true to prove that this is a homomorphism, but we've already worked that out before. Okay, and so a consequence of this theorem is, depending on what the characteristic of the codomain is, then R is either going to contain a subring isomorphic to the integers or to Z mod NZ, where n is the characteristic of the ring. So let's just think about this real quickly. If n is the characteristic of R, then, so let's suppose the characteristic of R equals n, and so then we have this map that sends Z to R. Well, what's the kernel of this map? Well, the kernel is going to be everything that is going to end up being, let's just say it, and we can talk about why that's true. It's going to be n times z. It's going to be everything, all the multiples of n in there. And that's just coming from the fact that phi of n is going to be sent to n times 1, which is equal to 0. And since n is the characteristic, this is the smallest thing. This is the smallest positive integer that's going to be sent to 0. And so since we proved in a homework assignment that all of the ideals of z are principal, and so that means that kernel of phi is going to be the ideal generated by n, which is nz. Okay. On the other hand, if the characteristic of R is 0, then phi of n equals phi of m. That would mean that n times 1 is equal to m times 1, which would mean that n minus m times 1 is equal to 0. And so since the characteristic is equal to 0, this means that n minus m is equal to 0, so n is equal to m. Okay, and so the kernel of this map is 0, and so this means that the map is 1-to-1. And so phi of z is going to be isomorphic to z. And so kernel of phi is trivial, which means, using the first isomorphism theorem, that z is isomorphic to the image of z. And so since that's a subring of R. Okay. Okay, and I'm going to close this video with one of my favorite theorems in all of mathematics. It's just called the Chinese remainder theorem. So we're going to be proving this for rings. The general theorem, if you've taken number theory, you've probably seen the Chinese remainder theorem for integers, but there is a broader, more general Chinese remainder theorem. And I actually prefer the algebraic statement of it. I think that it's much more elegant, and the proof is much more elegant because you can use the first isomorphism theorem, and it proves it very quickly. And so with the Chinese remainder theorem for ring states is that if you have R is a commutative ring with unity, and you have two ideals, I and j, such that I plus j gives you the whole ring, then R modded by the intersection of I and j is going to be isomorphic to the direct sum of R mod I plus R mod j. Okay, and so we're going to prove this using the first isomorphism theorem. And so the idea is that there are natural maps that we've seen before. And so let's call it phi, which sends R to R mod I. And we saw this before, where phi of R is mapped to the coset R plus I. And then another one, let's call it psi, that maps R to R mod j, where psi of R is equal to R plus j. And so then we can put these together, and let's make a map. Let's call it capital phi, that sends R to the direct sum, R mod I plus R mod j, where capital phi of R is equal to, gets sent to the coset R plus I, comma, coset R plus j. And so since phi and psi, since these are both homomorphisms, these are both the natural homomorphisms from R to R mod I and R to R plus j. Then this map phi, it's going to preserve both group operations in each component, and so that's going to make this a homomorphism between the direct sum. So this then is a homomorphism. So what I need to prove next is that, so we will show that this capital phi is onto, and the kernel of this map is the intersection of I and j. Okay, and so let's clear off some space and do that. So first let's show that this map capital phi is onto. And so since we're going to use the fact that here that I plus j gives us the whole ring. And so since this is a ring with unity, the fact that I plus j equals R, this means that there exists some I and j, such that I plus j gives me the unity. Okay, and so for any a plus I, any cosets a plus I, and b sub j, b plus j, then let's see, if I send, I'm going to send look at A times J plus B times I. And so where does phi send this element? Well, let's do it with little phi and little. Well, so little phi of AJ plus BI is going to equal AJ plus BI plus I, but BI, this is already inside of I, and so this is going to equal AJ plus I, right? But then what does J get mapped to? Well, I plus J is equal to 1, and so note that I plus J plus I, on the one hand, this is equal to, I plus J is equal to 1, so this is equal to 1 plus I. On the other hand, since I is in J, this is equal to J plus I. So J is in the same coset as 1, and so I can replace J there with 1 and get A plus I. And then for psi, similarly, this is going to equal AJ plus B times I plus J. But A times J is in J, so this is B plus I, B times I plus J. But I is in the same coset as 1, since J is in J. And so this is equal to B plus J. So big phi of AJ plus BI is going to get sent to the coset A plus I, comma B plus J. And so since these can be any cosets in each of these rings, then this shows that this is an onto map. So I've identified, given two cosets, a coset of I and a coset of J, we've identified an element in the ring that maps to it. Okay, so now that proves that phi is onto. So next we need to prove that the kernel of phi is the intersection, and that's going to be pretty quick, but first let's clear up some space. Okay, so let's suppose A is inside the kernel of big phi. Well, this means that little phi of A is equal to 0 plus I, which happens if and only if A is in I, and similarly psi of A would have to be 0 plus J, and this happens if and only if A is in J. And so we have that A is inside the intersection. And really this goes the other way as well. If it's inside the intersection, then for both of the small maps, psi of A and phi of A, it's going to be mapped to 0 plus I and 0 plus J, and so that would mean that it's in the kernel of the entire map. And so now putting this together, so we've determined that the kernel of phi is the intersection between the two. And so then we have that phi is an onto homomorphism. from R to the direct sum, R mod I plus R mod J. And so then by the first isomorphism theorem for ring homomorphisms, this means that R mod the kernel of big phi is isomorphic to R mod I plus R mod J, and we just proved that this kernel is the intersection between these ideals. And so that finishes the proof. That is all for this video. I will see you again soon.